Now we'll be going on to the next section, which is on transformers. Okay, at the end of this session, you should be able to describe the structure of a simple transformer and explain how does it works, and then solve problem using the turn ratio formula as well as the power formula, and describe the energy loss in cables and explain the advantages of high voltage power transmission. Okay, so this is under parts of Faraday's experiment as well. Okay, and in the first section, we learn about electromagnetic induction. We say that whenever there's a change in magnetic flux linking the coil, okay, induced EMF will be produced, and therefore an induced current will start flowing in the secondary coil. Okay, so over here is similar. Okay, we have coil A and coil B over here, and it's wrapped around a iron ring. Faraday discovered that when two coils of wire are wound on an iron ring, the magnetic field produced in one coil could induce a current in the other coil. Okay, so watch the animation. There's no animation over here, so we just go straight into the diagram. When the switch S is closed, the iron ring becomes magnetized and its magnetic field strength will increase from 0 to maximum. Okay, so the magnetic field is not constant or not uniform, it's increasing. Okay, because when you close the switch, the current increases from 0 to maximum, so the magnetic field strength also increase, but it takes place only at a very short timing. Okay, so the magnetic field lines linking coil B increases from 0 to maximum, and therefore there's a change in magnetic flux, and this change in magnetic flux will be linked to coil B and an induced EMF, and therefore an induced current will flow through this wire PQ, and therefore the galvanometer will deflect momentarily. Okay, it deflects only for a short moment, because only for the short moment when it's just closed, then there is a change in magnetic field and there's a change in magnetic flux linking with coil B. Okay, and the induced current, okay, stops, okay, and the compass needle will return back to its original position. Okay, so that is when you close the switch, and after some time it will go back to 0 again. Okay, once the current has stabilized, magnetic field has stabilized, there's no change in magnetic field, it will stop. But when the switch S is open, the magnetic field strength now decreases from maximum to 0, and again the magnetic field is non-uniform. Okay, the magnetic field lines in the ring linking coil B also decreases from maximum to 0, and because now there is again a change in magnetic flux linkage, now it's a decreasing magnetic flux linkage. Okay, again an EMF will be induced in coil B, and therefore a current will be induced in the wire PQ. Okay, but the induced current flows through PQ in the opposite direction, and therefore the compass needle or the galvanometer needle will again deflect, but now it will be deflected momentarily in the opposite direction. Okay, so this is the working principle behind a transformer. Okay, the magnitude of the induced EMF and the current can be varied by changing the number of turns on the coil around the iron ring, and therefore we come up with the transformer. Okay, so a transformer is a device that can change a high alternating voltage to a low alternating voltage or vice versa. So I can change the voltage from either high to low or low to high. Okay, so how does it work? Okay, the structure of a transformer looks something like this. Okay, there is two coils of wire. We call it the primary coil and the secondary coil. So like you need to go from primary school to secondary school, is the same. Okay, the voltage goes in from the primary coil, and then it comes out from the secondary coil. Okay, and then it's wrapped around an iron core, and take note that the iron core is laminated. Okay, we'll talk about why is it laminated later on. Okay, and yes, so these are the dotted lines are the magnetic field produced whenever there's current flowing in this solenoid. There's magnetic field generated, and this magnetic field will be linked over because magnetic field likes to pass through magnetic material, especially iron. So the magnetic field will be linked over to the secondary coil, and this, whenever there's a change in magnetic flux, EMF is induced here, and therefore current will flow in this external load. Okay, so the core comprises of thin sheets of soft iron insulated from one another. okay, is laminated soft iron core, okay, laminated, so it is insulated, and then there's two coil, primary coil and secondary coil, okay, and each coil has a certain number of turns, okay, and this, so the number of turns, for example, we call it N, okay, number of turns in the primary coil NP, and number of turns in the secondary coil NS. Okay, so NP and NS stands for number of turns in primary and number of turns in secondary. Okay, so we talk about the laminated soft iron core now. Why do the soft iron core, I cannot just use one whole big piece of iron core, but I need to cut it into sheets and then with insulation in between, or to laminate. Okay, the main purpose is to reduce energy loss, because what happens is, if you don't laminate the, or you don't cut it into sheets, there will be a lot of what we call eddy currents being produced. Okay, eddy currents are produced because eddy currents flows in circle. So whenever you have magnetic field and then there's soft iron, current will also be induced in the soft iron core, and this currents flows in circles. Okay, we call it eddy currents. We don't want a lot of current to form in the iron core. We want a lot of current, a lot of the energy to be transferred over to the secondary coil and to induce the current only in the secondary coil. So to reduce the energy loss due to eddy current, we cut the iron core into different sheets, thin sheets, and with insulation in between, so eddy currents cannot be formed. So there will be lesser energy loss. Okay, soft iron is always used because it's a soft magnetic material, is easily magnetized and easily demagnetized, so the magnetic field can be easily transferred, or the magnetic flux linkage can be easily transferred over to coil B, can be easily linked to coil B. Okay, and the number of turns on the coil affects the magnitude of the EMF produced. So it has two uses. Why do we use transformers? We use transformers in electrical power transmission from the power stations to our households and industries, and also before you use certain electrical appliances, some appliances do not allow high voltage to pass through, so it might damage the electrical components, so you might need to use a transformer to step down the voltage. Okay, we'll talk about step up and step down later on. Okay, so let's go through again. How does it work? So number one, there's a primary coil. Okay, the primary coil is connected to an alternating voltage. Why do I connect it to an alternating voltage? So for an alternating voltage, the current flows in one direction in one time, and then flows in the other direction at the other time. So this will help to create a changing magnetic field. I cannot be opening and closing the switch. Okay, it's not practical to keep open and close the switch in order to create a changing magnetic flux over here. So I want to create a changing magnetic flux, I can just use an alternating current attached to here. Okay, this will create a changing magnetic flux in the primary coil. Okay, so this alternating voltage will set up a varying magnetic field in the laminated soft iron core. Okay, and then this will be linked over to the secondary coil. The EMF, okay, will be induced in the secondary coil, and we call it the VS. So this one is the voltage of the primary coil, and then it will come out as the voltage of the secondary coil. Okay, so an induced EMF will be over here, and therefore an induced current will flow through this load. Okay, so we have NP, VP, NS, VS. Okay, the V stands for just the voltage at primary and voltage at secondary. Okay, so basically in transformers, okay, electrical energy is transferred from the primary coil to the secondary coil. Okay, the primary voltage and the number of turns in the primary coil is related to the secondary voltage and the number of turns on the secondary coil by the following formula. This is the turn ratio formula. Okay, so we know that as the number of turns increase, the EMF increases also. So as I turn more, I will have more EMF. So the same goes for here. Okay, so the voltage in the secondary is directly proportionate to the number of turns in the secondary. So the ratio will be equal. So the ratio of the secondary turns to the primary turns, okay, which we call it the turn ratio, will be equals to the ratio of the voltage in the secondary coil over voltage in primary coil. So I repeat again, more turns, more voltage, more EMF induced. So secondary turns over primary turns equals to the voltage in secondary over the voltage in the primary coil. Okay, so you can see this. Okay, so this is the circuit symbols for a transformer. So you have two coils of wire that looks like this. This one is the primary coil, followed by the secondary coil, and then one line in the center. Okay, so this one is the turn ratio, or the number of turns in primary coil and number of turns in secondary coil. Okay, so you have to take note, if my primary coil has got more turns, okay, let's say 100 turns in primary coil, and then the secondary coil only got 5 turns. So more coil means more EMF. It simply means that the voltage of the primary is more than the voltage of the secondary. So in this case, the one that comes out of the transformer is the secondary coil. You go from primary to secondary school. Okay, so the voltage that comes out of the transformer is the secondary one. If there's only 5 turns here, okay, so the voltage Vs will be much lower. We call it, so the Vp is more than the Vs. We call it a step down transformer. So the voltage is being stepped down from a high voltage, let's say 100 volts, to a low voltage, let's say 5 volts. So you can relate 100 turns, 100 volts, 5 turns, 5 volts. Okay, so I step down my voltage. It's a step down transformer. Okay, the same goes for the opposite way. If my number of turns in the primary coil is less than secondary coil, so let's say I have 5 turns here, primary coil, 100 turns in secondary coil. Okay, the same goes for the voltage. Then I will only have, if my primary coil is 5 volts, my secondary coil 100 turns, I have 100 volts. So the volts in the secondary coil will be much more. So the voltage is being increased. We say that is a step up transformer. Okay, so take note, there is step down and step up transformer depending on the turn ratio. The turn ratio is number of turns in the secondary coil over number of turns in the primary coil. Okay, because we are always interested in the secondary coil, the voltage that comes out. Okay, so by principle of conservation of energy, there is another formula. Power cannot be lost in an ideal transformer. In an ideal transformer means no energy loss. Okay, so we always say that how much power that goes into the primary coil will be equals to how much power that comes out of the secondary coil. So input power equals to output power. So we learn from power equals to VI. So the voltage of the primary coil times the current of the primary coil will be equals to voltage of secondary coil times the current of the secondary coil. Okay, that is if it's 100% efficiency, no energy loss. Okay, so Vs is secondary, and then Vp is primary, and then Is is current in secondary, Ip is current in the primary coil. Okay, so let's take a look at some work examples. Okay, a transformer has 500 turns in the primary coil and 250 turns in the secondary coil. The primary coil is connected to an input of 240 volts. Part A, is this a step up or a step down transformer? Okay, and what is the turn ratio? Okay, you may wish to pause the video and think for yourself for a few seconds. Okay, I will continue. So to determine whether it's a step up or step down, I need to think of the number of turns in primary and secondary. So I have 500 turns in primary and I only have 250 turns in secondary. So I have lesser turn in the secondary coil. Lesser turns means lesser EMF. So it's a step down transformer. Okay, and the turn ratio will be number of turns in secondary over number of turns. So you can see 500 is more than 250, so it's a step down. Okay, the secondary one is only 250. The turn ratio will be number of turns in secondary over primary. So it's 250 divided by 500. So the turn ratio is 1 to 2. 250 divided by 500. Okay, secondary over primary, number of turns, 1 to 2. Okay, and then next one, I need to calculate the output voltage. So the input is 240. So I need to use the formula NS over NP equals to VS over BP. Okay, so I want to find the secondary output. Okay, so the VS equals to NS over NP times VP. So it's 240 volts for the voltage of primary times, okay, 250 divided by 500, which is half. So I get 120 volts. So you see the turn ratio, 500 turns to 250. So if my input is 240, my output will be half of it because the turns is only half. So my output will only be 120. Okay, next one. But in most of the cases, our transformers are not 100% efficient. So in the case of a non-ideal transformer, okay, so reality, transformers are not ideal. For example, if 80% of the power input to a transformer is converted to useful energy, so we have the energy input to the energy. So we just zoom into the last part, okay? So it just means that the energy output over or the output power over the input power times 100% is the efficiency. So like for example, if this case is 80%, so 80% equals to output power over input power times 100%. Okay. Okay, so where do we use transformers? Okay, the main purpose of using transformers is to step up our voltage during transmission. So why do we need to do so? Let's take a look at this. Okay, so transmission of electrical energy. So this is the power station. In your power station, there's a lot of AC generator that generates a lot of AC. Okay, and AC is good because AC can be directly feed into the primary coil. The primary coil, I repeat again, you need an AC in order to create a changing magnetic flux. Okay, you want a changing magnetic field and therefore a changing magnetic flux that can link over to the secondary coil to induce a EMF in the secondary coil. Okay, so electrical energy generated at a power station is transmitted to the household factory using metal cables. So from power station to the household, you need to transmit through cables. Okay, but because there is resistance in the cable, there will be some energy loss when it's being transmitted from the power station to the house. Okay, and this form of some of the energy will be lost in the form of heat, okay, known as Joule's heating. And every time we talk about power loss, we use this formula I square R. Okay, I repeat, power loss, you use the formula of I square R to calculate. Okay, because the power loss is caused by the resistance and the current flowing through it. Okay, so to minimize energy loss, okay, the power loss is I square R. To minimize this power loss, I can do two things. Okay, method one, I can lower the resistance. So how do I lower the resistance? I can increase the thickness of the cable. So my R will drop, my power loss will drop. Okay, but increasing the thickness means the cable will cost very expensive. Okay, and there's a lot of cables throughout the nation. Okay, and therefore the second method is to, instead of reducing R, I can also reduce I. Okay, when I reduce I, the power loss will be even more significant because it's I square R. Okay, so second method, I reduce the current. So how do I reduce the current? We know that the formula power equals to V over V times I. Okay, if the power is transmitted at a high voltage, okay, so if I increase the voltage, my current will be very low. Okay, so if it's at a high voltage and low current, the power loss will be minimized. I repeat again, if the voltage is very high, I transmit at very high voltage, my current will be very low. And when my current is very low, my power loss, I square R, will be minimized. Okay, and when the current is lower, okay, thinner cables can be used. Okay, I don't need such thick cables, okay, because the current is very low. So this will also result in cost saving. Okay, so this is how our transmission of electrical energy works. Okay, so this is the power station that generates AC, okay, alternating current, and then is fed to a transformer. Okay, the main purpose of this transformer is to step up the voltage because I want high voltage, low current. Okay, I repeat, I want high voltage, low current. The power is the same. Okay, so step one, electricity produced in power station is stepped up by the step up transformer. So step up, okay, the voltage becomes very high, current becomes very low. Okay, and then number two is then transmitted along these transmission lines. Okay, so high voltage electricity is transmitted through the transmission cable. This is very good because high voltage, low current, power loss is minimized. Power loss, which is I square R, is minimized. So it's transmitted, transmitted, transmitted. Okay, then before I reach my primary consumers, secondary consumers, and your house, your factories, and all those, I need to have a step down transformer. Okay, because the voltage here is very, very high during the transmission, but I cannot feed such a high voltage to my household and my schools and my factories. Okay, all these step down transformers you can usually find it in your neighborhood. Your HDB flats below, there's usually a transformer station with the danger sign, and then in schools, okay, outside near the back gate or whatever, you should also see some transformers. Okay, so the purpose of the transformer is to step down the voltage now, okay, to make it safe. Okay, usually the voltage in Singapore will be stepped down to 240 volts. So all the electricity that comes out from your power plugs are usually 240 volts, but during transmission it will not be at 240 volts. It will be at a very, very high voltage such that the current is very low. Okay, so now before I reach, I will step down transformer will help to reduce the voltage to a suitable value for use. Okay, so some work examples. A 100 meters long transmission line has a resistance of 0.005 ohms per meter. Find the power wasted as heat in the line when 30 kilowatts of electrical power is transmitted at 240 volts as compared to at 120,000 volts. Okay, you can do a calculation and then later you will see that at 120,000 volts at high voltage, the power loss will be much, much reduced. Okay, so I'm interested in finding power loss. So the formula for power loss is I square R. Okay, I square R. Okay, so the first step, I can find the resistance first because I need I square R. Okay, I can find the R first. Okay, so the total resistance will be 100 meters times 0.0005 because 0.005 is ohm per meter. So I get 0.5 ohm. So this is the resistance of the transmission line. Okay, next one, I want to find I because I need power loss is I square R. I need to find I. So I have the power 30 kilowatts. Okay, part A is 240 volts. So I use P equals to IV. So 30 kilowatts is 30,000 watts equals to power equals to I times V, 240 volts for part A. So I get my current is 125. So power loss is I square R. 125 square times R, 0.5. So I get 7813. For part B, everything is the same. Okay, I work out that my current is very, very low because voltage is very, very high. Current is very, very low, it's 0.25. So the power loss is 0.25 square times 0.5. Okay, you can see much, much difference. This power loss is 7813. This power loss is 0.0313 watts. Okay, so it makes a lot of difference to step up the voltage before transmission to reduce power loss. Okay, next one. A transformer connected to a 240 volts mains is stepped down to a 12 volts to charge a car battery. So our power supply is 240. You need to step it down to 12 volts in order to charge this car battery. The transformer draws a current of 0.25 amperes from the main, and the maximum current that the battery can draw is 4.5 ampere. What is the efficiency of the transformer? Okay, so you think of the formula for efficiency. So efficiency is output power over input power times 100%. So I have the power, the volts and the current of both the primary and secondary, the input and the output. So you can calculate. So the output one, okay, is 12 volts times 4.5. Okay, step down to 12 volts and it can only draw 4.5 volt, 4.5 ampere. So it's 12 volts times 4.5. Power is V times I, 54 watts. Input power is 240 times 0.25. I get 60 watts. So it's output over input times 100%. So it's 54 over 60 times 100%, 90% for this transformer. Okay, next. A transformer with an efficiency of 80% converts an input voltage of 25 volts to 120 volts. The output of the transformer is a 120 volts 50 watts toaster. Determine the current in the toaster and in the primary coil. So in this case, it's only the transformer is 80% efficient. Okay, so immediately you should be able to see that the input voltage changes from 25 to 120 volts is a step up transformer. Okay, and this transformer is connected to this 50 watts toaster. So part 1, okay, so you have the output power, okay, which is 50 watts is equals to current P equals to VI or I times V. So it's I times 120 volts. So based on 50 watts and 120 volts, I can find the current in the toaster, which is 0.417 ampere. Okay, so now I want to find the current in the primary coil. Okay, I need to use the power, the efficiency and the power. Okay, so I have, because it's 80% efficient, so 0.8% of the input power is equals to output power. Okay, not input power equals to output. Okay, 0.8 times the input power equals to output power. So the output power is 50 watts. Come out to the toaster is 50 watts. So the input power is actually 62.5 watts. So I have the input power is 62.5 watts. I have the voltage of the input is 25. So I can use P equals to VI. So P equals to V times I. So it's 62.5 watts equals to V 25 volts times I. So I have I in the primary coil is 2.5 ampere.